Hi, welcome everybody to Deep Learning. Thanks for tuning in. Today's topic will be the backpropagation algorithm.
The stuff that works best is really simple.
So you may be interested in how we actually compute these derivatives in complex neural networks. So let's look at a simple example, and this simple example here is that we want to evaluate the following function. So our true function is 2x1 plus 3x2 to the power of 2 plus 3. And now we want to evaluate the partial derivative of f at the position 1, 3 with respect to x1. And there's two algorithms that can do that quite efficiently. And the first one will be finite differences. The second one is an analytic difference. So we will go through both examples here. Now, for finite differences, the idea is that you compute the function value at some position x, and then you add a very small increment, h, to x, and you also compute the original function position f of x, and you take the difference between the two, and then divide by the same value of h. So this is actually the definition of a derivative. So it's the limit between f at x plus h and f of x divided over h, and we let h approach 0. Now the problem is this is not symmetric, so sometimes we want to prefer a symmetric definition of this. So we, instead of computing this exactly at x and x plus h, we go half an h back and half an h to the front. So this allows us to compute exactly at the position x, and then we still have to divide over h. So this would be a symmetric definition.
And that was my 1987 diploma thesis, which was all about that.
Now, if you do that, we can do it in our example. So let's try to evaluate this. We take our original definition, 2x1 plus 3x2 to the power of 2 plus 3. We wanted to look at the position 1, 3. And let's just calculate this. Let's use the plus half h definition up above here. So we set h to a small value. Let's say a small value is 2 times 10 to the power of minus 2. And we plug it in. You can see that here in this row, so this is going to be 2 times 1 plus half of our h plus 9 to the power of 2 plus 3. And of course we also have to subtract our small value in the second term, and we divide by the small value as well. So this then lets us compute the following numbers. So we will end up with approximately 124.4404 minus 123.5604, and this will be approximately 43.999. So we can compute for any function even if we don't know the definition of the function. If we only have it as a module that we cannot access, we can use finite differences to approximate the partial derivative. In practical use, we use h in the range of 1 times 10 to the minus 5, which is appropriate for floating point position. Actually, depending on the precision of your compute system, you can also determine what the appropriate value for h is going to be. You can check that in reference number 7. We see that this is really easy to use. We can evaluate this on any function. We don't need to know the formal definition, but of course it's computationally very inefficient. Imagine you want to determine the gradient, that is the set of all partial derivatives of a function that has a dimension of 100. This means that you have to evaluate the function 101 times in order to compute this entire gradient. So this may not be such a great choice for general optimization because it may become very inefficient, but of course it's a very, very cool method to check your implementation. Imagine you implemented the analytic version and sometimes you make mistakes. then you can use this as a trick to check whether your analytic derivative is correctly implemented. This is also something you will learn in the exercises here. Really, really useful if you want to evaluate those functions.
And then I thought the most exciting thing is to solve the riddles of the universe, and that means you have to become a physicist.
Now the analytic gradient we can defer by using a set of analytic differentiation rules. So first rule is going to be the derivative of a constant is going to be 0. Then our operator is a linear operator, which means we can rearrange it if we have, for example, sums of different components. Then we also know the derivatives of monomials. If you have some x to the power of n, then the derivative is going to be n times x to the power of n minus 1. And the chain rule, so if you have nested functions, and you see the chain rule is essentially the important thing that we also need for the backpropagation algorithm, then you see that the derivative with respect to x of some nested function is going to be the derivative of the function with respect to g, and the time multiplied with the derivative of the function g with respect to x. Okay, so let's place those to the very top right. Yeah, we will need them on the next couple of slides, and let's try to calculate this. So here you see that partial derivative with respect to x1 of f of 1, 3. Then we can just plug in the definitions. So this is going to be the partial derivative of 2x1 plus 9. So we can already plug in the 3 and multiply it 3 to obtain the 9. And then in the next step, we can essentially compute the partial derivative with respect to the outer function, that is some variable z to the power of 2 multiplied with the partial derivative of the inner part of the bracket, that is 2x1 plus 9, and multiply the two with each other. So this is the application of the chain rule, and we introduce this new variable z. And the next step, we can then evaluate the partial derivative of something to a power of 2, where we have to reduce the exponent by 1 and then multiply with the exponent. So this is going to be 2 times 2x1 plus 9 times the partial derivative of 2x1 plus 9. So we can simplify this a little bit further. You can see that if we apply the partial derivative on the 2x1 plus 9, the x1 cancels away, so only 2 remains. 9 is a constant, also vanishes. So in the end, we end up with 2 times 2x1 plus 9 times 2. And now if we plug in 1, you will see that our derivative equals to 44. And in our numerical implementation that we evaluated previously, we were at 43.999. So we were pretty close. But of course, the analytic gradient is more accurate. Now the question is, can we do this automatically? And of course the answer is yes. We use those rules, chain rule and linearity, to decompose the complex functions of the neural network. And we don't do that manually, but we do it completely automatically in the backpropagation algorithm. And this is going to be more computationally efficient than finite differences.
There's something even grander. You can try to build a machine that isn't really a machine any longer, that learns to become a much better physicist than I could ever hope to be. And that's how I thought maybe I can multiply my tiny little bit of creativity into infinity.
So you can essentially describe the backpropagation algorithm in a nutshell here. You need for every block in this system, you need to, for every node, for every neuron, you need to have the inputs x1 and x2, and of course the outputs, that is y hat. Then you can compute in green the forward pass, and then you evaluate somewhere the loss function, and you get the partial derivative with respect to y hat. that comes in the backward pass, and then for every part in your module, you need to know the derivatives with respect to the inputs, here x1 and x2, and what we're missing in this function is of course weights. We need trainable weights, and the trainable weights, then we also need to compute the derivatives with respect to them in order to compute the parameter update. So for every module or node in this block, you need to know the derivative with respect to the inputs and the derivative with respect to the weights. If you have that for every module, then you can compose a graph, and with this graph you can then compute arbitrary derivatives of very complex functions.
You can write them down in 5 lines of pseudocode.
Let's go back to our example and apply backpropagation to it. So what do? Well, we compute the forward pass first. And in order to be able to compute the forward pass, we plug in intermediate definitions. So we decompose this now into some A. A is 2 times x1, and B, that is 3 times x2. And then we can compute those. Then we get the values 2 and 9 for A and B. This allows us to compute C, that is the sum of the two. The C is 11. Then we can compute E from that. That is nothing else than the power of 2 of C. This gives us 121. And now we finally compute G, that is E plus 3. So we end up with 124. Okay, now we need to backpropagate. So we see that the partial derivative of G with respect to E is 1. So we can compute that. This is going to be 1. Times the other partial derivatives. And now we need the partial derivative of E with respect to C. That's going to be 2C. With C being 11, this evaluates to 22. Then we need the partial derivative of C with respect to A. This is going to be 1. So we multiply with 1. 22 times 1 is again 22. And now we need the partial derivative of A with respect to x1. And if you look at this block, you can see that this partial derivative is going to be 2. So we have to compute 2 times 22, and this is going to be 44. So this was the backpropagation algorithm applied exactly on our example. Now we do have a stability problem because we multiply with potentially high numbers or potentially no numbers quite frequently in the scope of the backpropagation algorithm. An example for positive feedback and how it can lead to disaster is shown in this small video here.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. structure of steel and concrete can stand such a strain? Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
Now what can we do about it? Remember our feedback loop. We have this controller and the output where we compute the gradient. And you see that there is this value of eta. So if we have eta too high, it will create positive feedback. Then this will result in very high values of our updates. And then our loss may really explode. So we even, if our eta is too large, we even may have an increase in the loss function, although we seek to minimize it. What can also happen is if you pick eta too small, then you end up with the blue curve here that is called the vanishing gradient, where we just have two small steps and we don't get into a good convergence. So there's no reduction of loss. This is also a problem, vanishing gradients. So only if you choose eta appropriately, you will get a good learning rate, and the learning rate should start decreasing your loss very quickly, and over many iterations following this green curve, we should go then into some kind of convergence, and when we have no change anymore, we are essentially at the point of convergence on the training data set, and we can stop updating our weights. So we see that the choice of eta is critical for our learning, and only if you set it appropriately, you will get a good learning, a good training process. So let's sum up backpropagation. It's built around the chain rule. It uses a forward pass. Once we are at the end and evaluated the loss function, essentially the difference, then we can backpropagate this, computationally very efficient, using a dynamic programming approach. And backpropagation is not a training algorithm. It is just a way of computing a gradient. We will see more sophisticated training programs when we talk about loss and optimization in one of the next lectures. Some very important consequences are we have a product of partials, which means the numerical errors multiply. And this can be very problematic. Also because of the product of partials, we then result either in vanishing or exploding gradients. So vanishing you get when you have very low values, close to zero values, and you start multiplying them with each other, then you have an exponential decay. And if you have very high numbers, of course, you can also very quickly end up in an exponential function. Let's talk a bit about activation functions. So the classical ones are the sine function. We already had that in the perceptron. And now you can see that this is nice. It's symmetric. It's normalized between 1 and -1. But remember, we are talking about partial derivatives here. So the derivative of this function is a bit problematic because it's 0 everywhere except at the point 0, and there you essentially have infinity as value. So it's not really great to use this in combination with gradient descent. So what people have been doing is they switch to different functions, and one super popular one is the sigmoid function. So it's a bit S-shaped function, and what it does is it scales everything between 0 and 1. Using a negative exponential function in the denominator. And the nice thing is that if you compute the derivative of this, this is essentially f of x times 1 minus f of x. So this can also be computed, at least the derivative can be computed quite efficiently. In the forward pass, you always have to deal with the exponential functions, which is also kind of problematic. Also, if you look at this function between, let's say, -3 and 3, you get a gradient that may be suited for backpropagation. As soon as you go more away from -3 or 3, you see that the derivative of this function will be very close to 0. So we have a saturation, and again, you expect that you have a couple of those sigmoid functions behind each other, then it's quite likely that it will produce very low values, and this can also then lead to vanishing gradient. So what did people do to beat that? Well, they introduced the so-called piecewise linear activation function rectified linear unit, ReLU, which is the maximum of 0 and x. So everything that is below 0 is clipped to 0, and everything else is just kept. Now this is nice because we can compute this very efficiently. There's no exponential function involved, and the derivative is simply 1 if x was greater than 0 and 0 everywhere else. So there's much less vanishing gradient. We have essentially the entire positive half space that can be used for gradient descent. There's also some problems with the ReLU, which we will look in more detail when we talk about activation functions.
We are happy that it works better than any competing method, but that doesn't mean that we think we are done.
Okay, now you understood many basic concepts of the backpropagation algorithm, but we still have to talk about more complex situations, and in particular layers. So right now we did everything on the neuron level, and if you want to do all of the backpropagation on neuron level, it's very hard and you will very quickly lose oversight. So we will introduce layer abstraction and see how we can compute those gradients for entire layers in the next lecture. So stay tuned, keep watching. I hope you enjoyed this video, and see you in the next one. Thank you.